All right, let's continue on the problems in Ross and pick up with 5, 6, and 7. So again, I recommend you pause this video, you work through these problems, and then you check back to see if your solutions matches mine. All right, so number 5. For years, telephone area codes in the United States and Canada consisted of a sequence of 3 digits. Okay, the first digit was an integer between 2 and 9. The second was either 0 or 1, and the third was an integer from 1 to 9. How many area codes were possible? Okay, so we have these words again that signal to you first, second, third. So order matters, right? We have an order. The first digit is different than the second and different than the third. All right, so our first digit is an integer between 2 and 9. Well, there are 9 digits between 1 and 9 inclusive, so there are 8 digits between 2 and 9. So we have 8 choices for the first digit. The second was either 0 or 1, 2 digits for the second, and the third was any integer from 1 to 9. That's pretty straightforward and easy. That's how many area codes are possible. Part B is the same question, except we are starting with a 4. How many codes starting with a 4? Well, so instead of having 8 choices for our first digit, we only have 1 choice, right? There's only one way to choose 4. And then we have 2 for the second, 9 for the next. Pretty straightforward. All right, let's look at number 6. And 6 is very easy. It's a nursery rhyme. I once met a man from St. Ives. As I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kittens. How many kittens did the traveler meet? Well, this is just our step 1, step 2, step 3, step 4. We have one man who had 7 wives, and each wife had 7 sacks, and each sack had 7 cats, and each cat had 7 kittens. So the total number of kittens is 7 to the 4th. All right, let's look at one that maybe has a little bit more interest to it so far. The ones we've seen so far have been pretty straightforward and basic. All right, here, and how many ways can 3 boys and 3 girls sit in a row? Okay, so let's draw our scenario. We have 6 seats. There is an order imposed, right, because we're arranging them and they're different people, boys and girls. And so we really have 6 total, and we're just going to line them up. So you have 6 choices for the first, 5, 4, 3, 2, 1. That's how any of them can sit in any order together. In part B, in how many ways can 3 boys and 3 girls sit in a row if the boys and the girls are to sit together? Okay, well, we have 3 boys and we have 3 girls, and if the girls must sit with the girls and the boys must sit with the boys, then that means we have them split up this way. 3 boys and 3 girls, or 3 girls and 3 boys. We can't split them up any other way, or it'll split up the other gender. So we can either have, let's say boys are first, which means girls are second, and then once we have the boys here, we have 3 ways to put the first boy, 2 for the next, 1 for the last. And then if the girls are sitting over here, we have 3 in the first position, 2 in the second, and 1 in the third. However, we also can arrange, we could have the same situation except girls and then boys. So what we really have is this scenario right here times 2. Or, let's write it this way, 3 factorial times 3 factorial times 2. Okay? All right, I'm running out of room, so we're going to move up here to C. And how many ways if only the boys must sit together? So the way I like to think of this is the boys now get glued together. Okay, so let's say they are becoming 1 slot, and then we have the 3 other slots for girls. So one girl could be here, and then the 3 boys glued together could be second, then girl, 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 or they're first. or you could have girl, girl, and then the 3 boys glued together, and then girl, and so on. So what we really have is an arrangement of 4 objects. The 3 boys together, and then the 3 separate girls. So that is a 4 factorial arrangement of 4 things. However, just because they're glued together, we still have to account for all of their orderings. So for whatever position we have these 4, we have to permute the 3 boys inside. So it's 4 factorial to decide where the group of boys goes and their corresponding girls, times 3 factorial for every arrangement of the boys. Right, because you could have boy 1, boy 2, boy 3 in this position, or you could have boy 2, boy 1, boy 3, and so on. Okay. Lastly, let me come down here and erase some of this so that we have more room. D, in how many ways if no 2 people of the same sex are allowed to sit together? All right, well that means, since we have an even number, we have the same number of both, we either start with a boy or a girl. So if we start with a boy, that means we have to follow by boy, girl, boy, girl, boy, girl, boy. Wait, I think I have too many. How about that? There we go. Okay, so once we have decided, well, so the first, let me erase this here. So the first decision is who goes first, boy or girl. And there are 2, choose one way of who goes first, right? We either have a boy, there's 2 choices, a boy first or a girl first. Well, once that's decided, well then where boys sit and where girls sit are determined. But now you just have to permute their seats. So if you have boy first, you know you have girl, then boy, then girl, then boy, then girl. So we want to permute, the boys are fixed here, but they can sit in any of the order. So there's 3 factorial ways you can arrange the boys. Similarly, the girls' positions are fixed once you've decided who goes first, but you have to be able to permute the different girls. So also times 3 factorial. So 2 times 3 factorial times 3 factorial. And in fact, B and D have the same number of ways those things can happen. And that's it for 5, 6, and 7.